All right, guys, we are going to walk through and review our notes over theoretical, actual, and percent yield. So first, let's just start off with reviewing the actual vocabulary. So theoretical yield is the calculated value of the amount of product you should be able to produce in grams based on the amount of reactant. Okay, so remember with theoretical yield, the key word with this is calculated. So whenever you're asked for theoretical yield, you're doing this on paper, you're doing stoichiometry, you're calculating how much you should get. So in theory, whereas your actual yield is the measured amount So keyword would be measured. So that means I have it sitting in front of me physically. I take it and put it on an electronic scale. So it's the measured amount of product after performing the reaction in lab. So again, this value is going to be in grams. Okay, very specifically because I don't have anything other than a electronic balance, which only measures in grams. Okay, so that's why our theoretical yield also needs to be in grams, because down here with our percent yield equation, right, I'm going to look at the relationship between my actual yield and my theoretical yield. Okay, in order to do that, that means they have to be in the same unit, right? And we measure in grams. I don't measure in moles. I don't have something that measures in moles. So you always want to make sure theoretical and actual yield should be in grams. So my percent yield just lets me look at kind of how you did in the lab, how your reaction went. The higher your yield means more product, right? Which means that it did go better. There was less chance that something was lost or a mistake was made. So let's look at what an example of this would actually look like. So we'll walk through one together. So we've got magnesium reacts with oxygen gas to produce magnesium oxide. So remember in this, our oxygen, this guy is a diatomic element. So because it's by itself, it's not O, it's O2. Okay, and then magnesium oxide, in order to find your chemical formula, we have to find charge and neutralize. Because it's a +2 and a -2, I know if I have one of each, then it's already neutralized. So in this problem, you're actually given that already, and you're just asked to balance, but it's still good to reiterate. So looking at this, if you want to draw your particles, you can do that. Right, so I can see I'm going to use up my magnesium and one of my oxygens. Okay, but I still have an oxygen to use. The only way I'm going to use it up is if I bring in more magnesium. So now all of that is completely used up. I go back, put my coefficients. Remember, for oxygen, we only use 1, so you don't write the 1 because it's understood. Okay, so we successfully balanced. So we'll move on to the second part. Okay, so now we're getting into a conversion. So if you have 10 grams of magnesium, how many moles of oxygen gas do you need for the reaction to go to completion? So that just means how much am I going to need for this reaction to actually happen? So I would always suggest write out where you're trying to go. So we're in grams of magnesium, right? Remember with stoichiometry, special hint, if you're given grams of something, you're going to have to convert to moles. So I know I'm going to need moles of magnesium. And my end goal, I want to get all the way to moles of oxygen gas. Okay, now remember, in order to get from moles of one thing to moles of another, this is where we're going to utilize that mole ratio, that relationship between the two. And for my grams to moles, this is where we want to utilize our molar mass conversion. Okay, so for magnesium, the molar mass, I go to the periodic table and I see that for magnesium, my molar mass is 24 grams per mole. Okay, same thing as writing, for every 24 grams of magnesium, it is equivalent to 1 mole of magnesium. So that's my conversion factor when I take the next step and start setting this up. Okay, so I know that I want to get rid of grams. So I'm going to take that unit and drop it down to the bottom. And I want to get into moles, so that goes up top. Okay, so this is my algebra. If I've got grams times moles divided by grams, then I can see grams is going to cancel out successfully. So that's why each time I'm going to drag whatever I'm trying to get rid of down to the bottom in your setup using dimensional analysis. So remember my conversion factor up here, my molar mass. Okay, it says for 24 grams, there is 1 mole of magnesium. Okay, so now in my process, I'm here. Now I want to get into moles of oxygen. So I'm going to set up another conversion factor. Okay, so I'm going to find my mole ratios. Remember, this comes straight from my balanced chemical equation. So I can see for every 2 of magnesium, I'm going to need 1 mole of oxygen. Okay, so you could even write that out as a conversion factor and say 2 moles of magnesium is going to equal 1 mole of oxygen based on my balanced chemical reaction. So I'm going to take that and use it in my setup so I have my mole of magnesium that I want to cancel out. So I automatically drop it to the bottom, and I'm trying to get to moles of oxygen. Okay, so by doing this, I know my moles of magnesium is going to cancel out successfully. So I go back up to my conversion factor, go back to your coefficients. For every 1 mole of oxygen, I'm going to need 2 moles of magnesium. So when you guys are plugging this into your calculator, there's multiple ways that you could do this. It just depends on what pathway you want to take. So I can just put in my calculator 10 times 1 equals whatever my number is, divide by 24 equals, get that number, right, times 1, get that number, and then divide by 2 to get your final answer. So that's one way of doing it. Okay, you could also, notice, do everything up top. So 10 times 1 times 1. Okay, get that number. Divide by 24, get that number, and divide by 2 to get your final answer. Okay, you could also do all the math across the top and the bottom. So I see 10 times 1 times 1 divided by 24 times 2, right? So I would get 10 divided by 48, and if I just plug that into the calculator, you should get your final answer. So it does not matter which way you go about doing this process. You just want to make sure that you can successfully write this in your calculator, okay, so that we all are getting the same answers. So our final answer would be 0.21 moles of oxygen. So let's move on to the next. So based on the amount of oxygen gas, how much magnesium oxide will theoretically be produced? So remember, key word, theoretically. Okay, so that means on this question, I'm being asked to calculate the theoretical yield of my product, which is magnesium oxide. Okay, and remember, theoretical yield is always in grams. So in this problem, I'm going from moles of oxygen, and I want to get all the way to grams of my product. Okay, in order to convert into grams of your product, you have to know the moles of it first. So my first step here is going to be converting moles of oxygen to moles of magnesium oxide. And again, that's where we're going to use that mole ratio. And then when I go moles to grams, I'm going to utilize molar mass. Okay, so grams to moles or moles to grams, it's always molar mass. So let's go ahead, we'll bring down the amount we have of oxygen gas. Okay, I'm going to set up my mole ratio. I know I want to cancel out moles of O2, so we're going to drop that to the bottom. And I'm trying to get moles of magnesium oxide. Okay, I go back to my balanced chemical reaction, and I can see that for 1 mole of O2, I'm going to produce 2 moles of magnesium oxide. Okay, so I'll take those numbers, 2 moles for 1. Okay, and now I'm here, and I want to convert into grams. So in order to do that, I need to go and calculate the molar mass of magnesium oxide. Okay, so I know I've got 24 from magnesium's mass plus 16. Okay, so when you do your math there, we know that the molar mass of magnesium oxide is 40 grams per 1 mole. So again, you can rewrite this as a conversion factor. And now I can utilize it in my conversion. So I know I want to cancel out moles of magnesium oxide. So that's going to drop down to the bottom. And I want to get into grams. Okay, so whatever you want always goes to the top. Whatever you cancel goes to the bottom. So I go back my conversion factor here. So I want 40 grams per 1 mole. Okay, so again, however you want to calculate it is completely up to you, right? If you want to do it step by step, you can. If you want to do it all out at once, you can. So when I calculate this, you should get 16.8 grams of our magnesium oxide. So remember, this is my theoretical yield. So in theory, based on the amount of oxygen I'm going to use, I should get this much magnesium oxide. Okay, so the only way I'm going to know how much I actually get is by doing the chemical reaction, right? Or being told the actual yield, looking at data to identify that for myself. So the last problem is asking us to find percent yield. So remember, percent yield is your actual divided by theoretical times 100. So of our magnesium oxide, and it tells me that I actually obtained 5.75 grams after completing the lab. Okay, so I'm going to go ahead and set this up. So your 5.75 grams, divide by our previous answer. Okay, and I can already tell that it's not exactly a stellar percent yield. So you should get about 34% yield of magnesium oxide. Okay, so it looks like there was a significant loss in product. So as the last kind of step with your theoretical actual percent yield problems, it asks you, so what does that actually inform you, right? So we know that things were lost. So there's definitely a loss of product. Okay, a big reason for that could be that there was no closed system. Okay, or when you are mixing chemicals, maybe some stuff got left behind. I know we talked about in class, if there is heat involved, if you get something hot enough, it can start to evaporate. So that's something to keep in mind as well. So that is our review of theoretical, actual, and percent yield.